Hello, class. I am back to do a great lecture on a great topic, the beginning of what I call mechanics of solids and what a lot of other people in this day and age call strength of materials. Really, it has both names. So, but I taught this at Purdue, and I also taught this at the University of Missouri when I was there doing a sabbatical on broadcast, teaching methodologies. That was a long time ago, and before I taught physics and before I taught electrical engineering. I have degrees in both mechanical and electrical, so I don't have a degree in physics. But I mainly taught, thermal physics and, fluid mechanics and, more physics-related types of things when I was teaching in physics, as I was predominantly teaching engineers, although I was also teaching, beginning physics, physicists and stuff too. Anyway, let's get back to this. This is really stress and strain, strength of materials. And where we want to start off first is because we kept using this, stress and strain, why not start off with that? What is stress? Stress is force applied divided by cross-sectional area. And let's draw some kind of, it could be, like I say, could be a circular cross-section. It could be a rectangular cross-section, right? I'm just going to say it's a rectangular cross-section, and I've got a force pulling on it at both ends, P. Now, we're actually going to do, in a little while, we're going to do an example problem looking at what would be the minimum cross-section of a beam that would support a walkway at a mall. And in fact, you're probably thinking, oh my God, is he going to do a case study of that collapsing walkway at that mall in Minnesota? No, I'm not. I don't even know about that. I've never even heard of it. No, I'm kidding. Of course I've heard of it, but it's not an exact duplicate of that. But I do want to point out, what happens, when you don't take safety factor into account and really design for safety with a safety factor. And in fact, all coaxial cables that you have now have a braided outside ground shield, right? Does everybody know what I'm talking about when I'm talking about coaxial cable? Coaxial cable usually has a center conductor, and then, it's got an outside ground shield. If you've ever chopped your, coaxial cable in half, don't do this with your cable. Do it with the neighbors. I'm kidding. The outside is a ground shield, isn't it? So it's actually a braid. It didn't used to be. It used to be aluminum foil. And then there was a fire in New York City, and a woman tried to save herself with her coaxial cable. And thank God she was saved. Her and her baby were saved by a fireman. But it dramatized, I'm sure that's a word, it dramatized the need for having these coaxial cables that are in everybody's house be ropes, right? So basically this can hold up, or they say it can hold up 180 pounds. So if you're 180 pounds or less, then I haven't turned this off, have I? Thank God, no. If you're 180 pounds or less, this thing could hold you up, but it's got a safety factor of 2. So literally, if it had to, it could hold up 360 pounds, or 2 people going down on the rope at once, on the coaxial cable at once, right? So that's what I wanted to point out. And you're going to look at coaxial cables a lot more when you start to get into electromagnetic field theory and metallic conductors and stuff like that. I teach that course senior year. Eventually, I'll have you for that probably. Now let's get into this too. So that's stress, and this is going to be the force I've got here, newtons divided by square meters is going to give me pascals, or kilogram per meter second squared, as I've said before. Now that's our stress. What is strain, right? So we know what stress is now. That's the definition of stress. What's strain? Strain is my elongation or my deformation divided by my original length. So let's look at this again, but let's look at it in sort of a cross section now, or a two-dimensional representation, right? Let's say that that's my bar, and I'm pulling on the bar at both ends, right, with a force P. So what's going to happen to that bar? I think everybody can see, and I'm going to, exaggerate this obviously, but the bar is going to extend, isn't it? Right? The bar is going to get longer. That's what happens with a rubber band. So why wouldn't it happen with a piece of steel? So there you go. That's exactly what happens. And this extra little bit that I've got here is called delta, right? And then this part right here is my original length. Does everybody see how I've got that? So strain is my extension or elongation, and L sub 0 is the original length of the tensile specimen that I'm pulling on. This thing is going to get a little bit longer. I'll try to draw it in 3 dimensions. I'm not going to promise anything, but let's say that maybe this once I will actually get it right. See how that is now? It's getting longer. That's what I want to point out there. And that distance is the delta, and this L sub 0 is back here. So that's what we've got. That's stress and strain. Now when you look at stress and strain, a stress and strain curve, because you've probably all pulled on a piece of steel, and ripped it in half with your hands like Superman, or not. But you've probably done it with a piece of plastic, like a plastic bag or something like that, right? So what does it look like? Let's look at a stress strain curve. When we say stress strain, couldn't we really say that the force applied, right? So this could be a force applied and a deformation graph, couldn't it? I apply a force, and what is my elongation? In fact, let's call that, usually it's under tensile stress, it's called elongation. If it's an extension, and it's called, contraction if it's a contraction. But either one is called a deformation. That would be the superset. An elongation is a positive deformation, and a contraction is a negative deformation. So let's just look at our force applied and this. But really, couldn't we say that this graph would also represent force applied divided by cross-sectional area? I mean, if we're not talking about a scale, right? It could be this, because all that is dividing by a constant, isn't it? Wouldn't it be it'd be a different scale, but it would be the same relationship. And this over here, the elongation, we could plot that, but couldn't we also plot the elongation divided by the original length? Because let's face it, the original length is just a constant, isn't it? So force times elongation, stress, strain are the same thing. So I'm going to call this a stress, and this is what it is called, strain diagram. Now I'm going to go through all of the diagram, you know, the whole diagram, but we're only going to be interested in the very first part. We're going to be interested in the linear part. So let's say that I've got a piece of titanium. Titanium looks like this. That's what titanium looks like. I'll call that A. So A is titanium. You see it has a very sharp angle right there, right? Steel. What does steel look like? Steel looks like this. Depends on the type of steel. It looks very much like titanium, doesn't it? Except this front part here is got a slope to it that's much shorter, right? It's not as high. It's a shallower slope than that first one. So that would be B, and that would be steel. How about something like bronze? Well, I don't know, bronze, brass, that'd be about the same. Copper. Copper would look like this. Right? Copper is much, much softer, much more ductile. In fact, this copper thing would actually go quite a ways out here. I can't really draw it. I should get rid of that thing. However, I want to talk to you about these. All of these are crystalline metals, right? Titanium is a crystalline metal. Copper, crystalline metal. And when I say crystalline metal, I really mean body centered cubic, face centered cubic. This happens to be face centered cubic when you're talking about copper. I'll put C there, just Cu for copper. And but what about aluminum? Aluminum is a bit different. Aluminum looks like this. Right? Aluminum doesn't have a really well-defined yield point. That's right, this part right here, this point, this point, this point, those are all called yield points. And we've got two different yield points. We've got the upper yield point and the lower yield point, right? Two different points. If I was to blow it up here, it would look like this, this, like that. This would be my upper yield point, and this would be my lower yield point after we've had some shifting and a lot of defects flowing toward the edges of the individual crystals and grains that we have there. So you go up, and then there's two different regions there too. Two different regions. For better use the orange. For this, right, this region right here where it's all, I'll draw some rubber on there too. Here's what rubber would look like. I know, it looks like rubber too, doesn't it? That's what the yield thing of rubber is sort of like. So that's rubber at the end. And what do I call it? E. So D is aluminum, and E is rubber. Yeah, and you know that. So anyway, this is my stress strain diagram. We're only going to be interested with everything to the left of this. This is my elastic region, and this is my plastic region. It has nothing to do with plastics, of course. We named it plastic long before plastics came around. So this is the elastic region. So let's just look at that again, sort of blowing that up a little bit. Because that was becoming very messy. So here's my stress, here's my strain. I'm just going to look at, I'm just going to expand out, because we're not so interested in the plastic part. In fact, what happens is, as I pull on this, it starts to, up until this point right here, in the elastic region. In fact, let me draw this. Right, let's say that then continues on, right? But this is my elastic region. Right here, right where it's linear, that's called my elastic region. And we have some rules as to how material, works in this region, especially in the linear region. Now, later on, when we got onto the plastics, you have an extra thing where, basically there's movement in the crystal grain structure in the material, and defects are running toward the sides, and eventually they pile up, and we eventually get, decrease in cross-sectional area, and then eventual failure, right? So we're not worried about that part at all. Again, that is the plastic region, and that is for grad school. Right now, we're just worrying about the thing. And you know what? You know what Hooke realized a long time ago? That's a straight line, right? It's a straight line. And it has a slope, doesn't it? So that straight line that has a slope, we can see there's a relationship between sigma, or stress, and strain. So if I have a straight line, I know that y equals mx, right? And I have the same thing here. I've got a straight line, so I know that sigma equals something epsilon. And that something we call the modulus of elasticity. Of course, that's the slope. That's the slope of the line, isn't it? It's the slope of this line right here. This is called Hooke's law. Whoa, I don't even know, can I get a Nobel Prize for coming up with that? Hooke did a great thing, though. I mean, this was way when he first realized all of these things. Nobody had realized it. They were still trying to, think about keeping the fire going in the hearth. Now we don't even know how to spell hearth correctly. Anyway, let's go on. So this is it. This is Hooke's law. You'll also hear the modulus of elasticity referred to as Young's modulus sometimes. Young actually did do a lot of great things. At first I thought he was just an usurper stealing Hooke's thing, because basically he's just naming this thing after himself, after Hooke. He was Hooke's assistant, but he went on to do some other great things too. I can't remember off the top of my head what they were. Anyway, Hooke's law tells us a few things then, doesn't it? Because I know that sigma equals P over A. And I know that equals E times the deformation in length over the original length, right? So why don't we solve for the extension, the elongation? So the elongation is going to be, well, let's see what we've got here. We've got P, we can bring the L up there. So that's PL over A. Well, let's see, we got the E in the numerator, and that's in the denominator. So bring that down there, AE. Now, you're probably saying, well, he didn't have to explain all that. No, of course I do. I've got to see people, up with it. Otherwise, people looking at it, I just write it down. They're like, what? Where did he get that? let's do the algebra. Right? Let's do the algebra in class. We'd be doing it together. I'd be making sure everybody was there. I'd be asking somebody from class, okay, if we've got this relationship, what does delta equal? And you would be doing the algebra in your head. And that's the way that, everybody should learn. We can't do that right now, but soon enough, we'll get back there. All right, now, so that's the deformation. That tells me how long that thing, would be. Now, I want to do a little example, just talking about a walkway in a mall, and I want to talk about this and the safety factor, right? Because I talked in the last lecture about the importance of safety factor and how that could change things, so much. So let's say that for this problem, we're going to analyze it without, with the safety factor equal to 0 and a safety factor equal to 2. Actually, let's just say safety factor equal to 1. If it was 0, that would be no safety factor. So we're not going to use, in other words, we're not going to use the safety factor, or we're going to use the safety factor of 2 to design this walkway, this small walkway support system. That's what we're going to do. All right. So we're going to use a support column. We're hanging this stuff from the ceiling. We're using the same epoxy that was used in the tunnel for the big dig. So we're planning on everybody being killed, and of course everybody was, but like 180 people were injured. I don't know how many people were killed, but this is what they did. And of course it pulled the epoxy out of the ceiling. That's how the whole thing failed. The bars themselves did not fail. So our design right here did not fail. All right, we're going to use a material, steel. And the maximum, before failure, the maximum stress that steel can withstand is 240 megapascals. All right? So it's a good steel. It's not like we're using some cheap steel or cheap epoxy, which was the real culprit in the crash anyway. We're going to say that each one of these is going to have to hold up 1,000 kilograms. And in fact, when you saw the collapse, you realized that they were so overloading that, but it wasn't an unforeseen overloading. It wasn't an unforeseen overloading. They were having, I think, a children's choir. So all the parents were, standing on the walkways, far exceeding what a walkway should be. Walkway should, handle some moving traffic of 10, 15 people at any one time. This thing must have had 200 or 300 people on each of the two walkways that were one right above the other. Couldn't have been the worst epoxy failure ever. So they have to hold up 1,000 kilograms. All right. So we want to look at this in two different ways. So first of all, because we're designing this, and what we want to find out in the end is, what is the radius of these steel supports. We're going to use circular steel, not rectangular steel like we've got up here, something that's more like a coaxial cable, but we don't know. We've got to figure out what the radius of it. That's what we're trying to find out. So let's go back to this. We know that this is a maximum, and we know that 1,000 kilograms, if we look at that, and we're looking at the force that's going to apply, the force is going to be 1,000 kilograms, right, times 9.81 meters per second squared, right? So this gives us 9,810 newtons. So that's the force. Don't worry about the mass. Think of the force that the thing has to withstand. So what we know is that if that's P, and that is going to be our maximum 240 megapascals, then we can quickly figure out what A is going to be, because A, right, is just going to be my stress. Wait a second. Yeah, P over my stress, right? And so 9,810 newtons divided by 240 megapascals. I'll just newtons divided by 240 megapascals. Boy, I got that in there. Isn't that great? So that's what it is. P divided by sigma. And that gives us a cross-sectional area of 41 times 10 to the minus 6 square meters. And what that implies, if you think about it, because you know that that's going to be pi r squared, right? So I've got pi r squared, and so that tells us that r for n equals 1, right? This is the radius. If we're not going to put any safety factor in here whatsoever, that's going to come out to 3.61 millimeters. And that means that the diameter is going to be, and this would be the n equals 1, no safety factor whatsoever, would be 7.2 millimeters. So about 3/4 of a centimeter for each one of those steel rods to hold up those walkways in the mall. All right. Now, that is, like I say, that is, I'm going to put n equals 1. And then I'm just going to draw a line under this for a second. Now, how about n equals 2? What we could do is we could cut this in half, couldn't we? We could say that, well, that's just 120. You know, couldn't we also say that if we got over here that we've really got 2,000 kilograms on each one? We could do it that way too, couldn't we? We got 2,000 kilograms, but we keep this the same. It works out the same, right? If I double this, or if I cut this in half, it's both going to come out to the same number. The way I look at it is I'm going to double the amount that's on there. So, because I'm using the same type of thing, let's double that. That's where the 2 comes in. I'm going to double the amount of force. Instead of 1,000 kilograms, I'm going to think it's 2,000 kilograms, right? So 2,000 kilograms, and that implies 9810 times 2, just a second, 19,620. 19,620 newtons, and of course I'm still using the 240 megapascals that I have there, so that gives me an n equals 2 cross-sectional area of 8.2 or 82, excuse me, 82, which is just going to be twice what this one was, times 10 to the minus 6 square meters, right? So I'm going to have twice the area that I would have had, and what that implies as far as the radius, and this is the radius with n equal to 2, that's going to give me 5.11 millimeters, or a diameter for n equals 2 of 10.22 millimeters, or about 1 centimeter. So a diameter of about 1 centimeter compared to a diameter of about 75 or 7.2 millimeters. See, so we're not beefing it up. We're not doubling the diameter here, because if you look at the ratio, the relationship between the radius or the diameter and the area, it's not a proportional relationship, is it? It's a polynomic, God, what am I? Quadratic. So, or parabolic spandrel is what it would look like. So what we've got down here, we just doubled that. All right, I just wanted to look at that for a second. Now, how long would these be? Right? Either one of these two, if I was to put those types of loadings on them, how much longer? Let's just look at this with n equals 1. Right? So delta, or the elongation of that, is going to be, oh, you know, I have to give you an L0 for the elongation. I think it was 5, excuse me. I think I used 5 meters. Actually, I've got another one here that probably is better at doing that. I'm going to use this one. Yeah, because this also uses a 10,000 kilonewton force. And I'm going to say that I have a circular bar. Now, I can't draw the full length of this bar to scale because this bar I'm going to make 5 meters long. Right? So it's 5 meters long, but it's relatively thin. It's only 5 millimeters, or actually, I'm going to write a diameter here. It's going to be, for diameter, 1 centimeter. So basically 5 millimeters is the radius. So the radius, that's the diameter, and the radius is going to be, in fact, it's very similar to this one, isn't it? So the diameter is 1 and the radius is going to be 0.005 meters, or 5 millimeters. In fact, the 5 meters that I have here is this, but and I did, let's see, I put 10,000. Yeah, I used this n equals 0, so, or n equals 1. So this is really where we have no safety factor, and we're looking at these because these were about 5 meters long. And I'm going to use the equation PL over AE. And for this, I'm going to say that E equals 80 gigapascals. Now, you know, what is E? E is the slope of this line, isn't it? And it's going to be the rise over the run. So you could say that E equals, if we wanted to look at it, sigma over epsilon, or the way that we usually write it is like this, right? Yeah, there you go. Okay, so let's just put those in there. So P then is going to be the force that is pulling down on this, and I said that it was, I can use the 9,810 newtons that we have. Let's do that. And then the length is 5 meters. And then the cross-sectional area, well, we had that before. I'm just going to put pi times 0.005 meters squared. And then E is 80 gigapascals, right? And so now we have, that's a 5. If you can't tell, that's a 5 squared, and times 80 gigapascals. And so now that should give us the elongation for that. And I'm just going to pop it in here again just for a second, but I've got it written down there as to what it was. But I did change that 10,000 to 9810, so that will change the answer a little bit, but shouldn't change it too much. Just a second. There you go. So I get 0.007865, but I'll say 7. Now, really, that is 4 significant digits, right? Does everyone see that? 4 significant. So those 2 zeros, those aren't significant at all. I just want to point that out to you in case you haven't had the thorough understanding of significant digits yet. So those are only my 4 significant digits right there. So you'll say that it's 7.8 millimeters, right? 7.8 millimeters. That's almost a centimeter. So when this thing is all loaded up, it's almost a centimeter longer if it has the full 10,000, 1,000 kilograms or 10,000 newtons on it. It's going to, have be quite a bit longer, almost a centimeter longer. And you're thinking a centimeter, that's not much, and you're right. Centimeter really isn't much, and this is when we're totally loading it. Usually if we were loading it normally, it wouldn't have any of this on there. This is when we're expecting parents. Now, I also want to check, does it go over the maximum for theta? So if we do that, it's just going to be the force that's applied, and I have 9810 newtons, right? And then the cross-sectional area for this is just going to be pi times 0.005 meters squared. I hope everybody can see that 0.005 meters. I'll just say it again too, squared. So let's just do that. 9810 divided by pi divided by 0.005 squared equals 124.9. I'll say approximately 125 megapascals, right? 125 megapascals, that's not a point there. Yes, so it's much less than the 240 megapascals, isn't it? Is it less than half of that? Do we still have the n equals 2? No, we don't, do we? We still don't have the n equals 2 there, but this is more or less how the thing was laid out. Okay, I thought I'd just point that out. We're going to go on to another lecture. I don't know, maybe tomorrow morning, but going on to another lecture after this, and we're going to continue in this vein, except that we're going to start getting into Poisson's thing, and we're also going to get into shear stress. Right now, we've only talked about normal stress and normal strain. In the next lesson, we're going to talk about shear stress and shear strain, and also Poisson's ratio, and how shear and normal stresses and strains are related to one another. All right, see you there.